So just like when things aren't equal, right? That's basically when we hear about inequalities. But so inequalities in general, it means when things aren't equal. And in mathematics, in problems, it's usually a comparison between two values, whether it's less than or greater than. Some inequality notation we'll use is greater than, less than, greater than or equal to, less than or equal to, and not equal to. Is everyone familiar with this notation? If everyone has a good idea of what everything means, I'll just jump ahead and we can go a little bit faster. If not, you can feel free to private chat me or anything. So I just have a good idea. Okay. Cool. Okay, from what I'm seeing, I think everyone has a good idea, so I'll just leave that as a reference and yeah. And just a heads up is that today we'll be talking mainly about non-negative real numbers, and real numbers are just referring to numbers that can be represented on a number line, and non-negative is just anything equal to or above 0. And that's basically all the notation and stuff we'll be using today. Okay, so some examples of basic uses of inequalities. So in a problem, if it mentions something about maximum or minimum value, usually inequalities can come in handy, especially if it's if we see like polynomials and stuff like that. So there are 2 quick exercises down below. I'll give you guys like 2 minutes to do them, and feel free to like share ideas in the chat. But it hopefully everyone is familiar with it. Yeah, okay. I'll give you guys 2 minutes to do it, and then we can discuss really quickly. And feel free to, if you have any answers, just share it to me. Or just share it like in the main chat. I think that could be helpful for everyone as well. Yep, I'm getting some good answers. All direct message. Yeah. I think everyone should have some confidence. You can send it in the main chat. They're good answers. Okay. Okay. Yeah. Yeah. Okay. Yeah, I think we can quickly just go over it. So what probably for the first one, everyone did is probably plus 27 on both sides, make it 16x greater or equal to 48, and then you can divide both sides by 16 to get x greater or equal to 3. So in this question, it does ask for the minimum value of x, so that in that case, it would just be x equals 3. And for the second one, I think everyone would have just added 1 to both sides, right? And then you'd notice it's x squared plus 4x plus 4 smaller equal to 0. And that's like a square number, right? Like you can factorize that into x plus 2 squared, smaller equal to 0. And that sort of idea leads us into the first inequality we'll be covering in today's session, which is the trivial inequality. It's called trivial inequality because, as I'm sure most of you probably will know it and be really familiar with it, as it is pretty trivial. It just says that the square of all real numbers is non-negative. So if x is a real number, then x squared is greater or equal to 0. And equality for x squared equals to 0 only happens when x is equal to 0. And this very basic inequality is actually very useful in many cases for like generating, like creating square numbers to show like a relationship between different in an inequality. So we have a problem below, and that's proved that 3x squared plus 2y squared plus 2xy plus 10x plus 6y plus 22 is greater than 0. Okay. I'll give everyone like 2 minutes to think about it. It is in the handout, all the working is in the handout, but we will go over it together. So feel free to give it a shot before looking at the answers in the handout. And then we'll go over it together. So I'll give everyone around like 1 to 2 minutes to do that. Just have a look at it. Okay, I think we will begin. Okay, does anyone have any ideas towards like the first bit? I've seen some good ideas in yes, okay, I've seen some really good ideas. Okay. Just to make sure, does anyone hear an echo? Is this sound all right? Okay, yeah. Cool. Okay. Yep. So I've seen some good ideas of first trying to put the 2xy in a square, right? Because we don't know. Okay. We don't know whether x and y are positive or negative numbers. So if we can put in a square, that can help us show that it is actually part of a square. So I saw some people do something like this. Right? Okay. This is a good first step. And then what we can do is something like this. Okay. And there are some different ways you can go from here. What did people have in mind? Yeah, okay. So what I will do is I will do the method where we make everything on our left-hand side into squares. And we can do that by noticing that this sort of fits into a square, right? Like we can make that into a square with y, and what we can do is this. But notice that we did add a 9 here, so what we have to do is we have to take it away, right? So 22 minus 9. Yep, and then factorize that into a square, and we get something like this. I think my screen is frozen. Just give me 1 second. Okay, cool. This should be better. Okay. Yep, so now we've formed 2 squares, and then we only have, what is really good right now is because we only have x left, and we don't have to worry about y anymore. But how can we factorize this further into preferably like squares? We can do this by like completing the squares as well, with leaving it in another form, but what we will do is we can notice that 2x squared plus 10x plus 10 is equal to right, this is one way we can do it. If we notice this, then that's really good, right? We can just write it as, yep. And then we can change our entire left-hand side into, and now we have all squares on our left-hand side. And then by the trivial inequality, we know that the left-hand side has to be greater or equal to 0, right? But this isn't a greater equal to sign. So it's actually a strictly greater than sign. Does anyone have any idea as to why that it can't be equal to 0? Why our left-hand side cannot be equal to 0?
X plus 3 squared and x plus 2 squared is always greater than 0.
Yeah, okay, I heard something really good. Yes. So if we did want our left-hand side to be equal to 0, it would mean that every single one of these squares has to be equal to 0, because every single one of these squares individually is greater or equal to 0. But how can you have x plus 3 squared equal to 0 and x plus 2 equal to 0 at the same time, right? Yeah, okay. We cannot happen at the same time. So equality cannot be achieved. Right. And yeah. Does anyone have any questions? Hello? Can everyone hear me? Okay, yeah. Does anyone have any questions towards how we did it? I know there's another way you can do it that would kind of start a little bit different from this step. So if you just like made this into a complete square form, you would also get that it's strictly greater than 0. But if we wanted to use the trivial inequality to the fullest extent, we can also do the way we did below. Okay, so I'm going to say there's no questions. Okay, cool. Then we can move on. Okay. So that's the trivial inequality. Now we'll move on to the AMGM inequality. So this is a really, really useful inequality in a lot of problems. And what AMGM stands for is arithmetic mean and geometric mean. So, and we have to note that when we're using this inequality, it has to be for non-negative real numbers, so they cannot be negative. So first, we need to understand what the arithmetic mean is and what the geometric mean is. So arithmetic mean is what we would commonly regard as an average of a sequence of numbers. And say we have a sequence of numbers x1 plus x2 plus x3 all the way to xn. So there's n numbers in the sequence. Our arithmetic mean can be just expressed as it says below. So x1 plus x2 all the way to xn divided by n, right? And geometric mean, you guys may be a little less familiar with. So how you get it is basically it's an average of the product of the sequence of numbers. So instead of addition, we're looking more at multiplication. And we can obtain it by like multiplying our sequence of numbers together and then using the nth root and taking the nth root of it. And I believe everyone is familiar with like higher order roots. So it could be like square root, it could be cube root. It just really depends on what the value of n is and how many numbers there are in our sequence. Is there any questions towards what the AMGM like respectively are? I'm super happy to explain a little bit more or give some examples as to how we actually find things like the geometric mean of a sequence of numbers. I'm taking that as everyone understands. If anyone has any questions, okay. Okay, cool. Let's look at how a geometric mean could be used for like just an example of how we use it, right? Let's pick some numbers. Let's say we have numbers 1, 5, 12, 22. Okay, maybe the number's a little bit big. Let's go 20. Okay. Can anyone tell me what the geometric mean of these numbers would be? So by the formula we had before, what would our like multiplicative average be? Okay. Yeah. Okay. Yeah. Okay. I wasn't expecting like people to actually calculate it, but yes, the process would do to like obtain it is something like we have 4 numbers, right? So in this case, essentially our n would be 4 because in our formula before it was like x1 plus x2. Oh wait, no, that's sorry, my bad. Times xn to the nth root, right? So in this case, n is 4, and what would basically use is the order 4th root, and then it's 1 times 5 times 12. Like, yeah, and that would just be 1, 2, 0, 0, I think. Okay, yeah. And I wasn't expecting people to actually calculate it, but that's how we'd get the geometric mean, right? So everyone just knows how we'd actually use it. Cool. And we'll move back. Okay, so this is what the arithmetic mean and what the geometric mean are. Then what the AMGM inequality actually states is that for any sequence of non-negative real numbers x1 to xn, the AM of the sequence is greater or equal to the GM of the same sequence, right? So it can be expressed algebraically as what we see below. And it's important to note that equality can only hold if we have that x1 equals x2 all the way equals to xn, right? So they all have to be equal. And you can try that out, like what happens if they are all equal, and you'll just notice that, oh, your left-hand side is just like x1 or whatever, and your right-hand side is also just x1. And that's not too hard to see. So let's try a natural problem. And as we see below, again, I'll give you guys like a few minutes to think about it. And it'd be really good if people did share some ideas just in the chat with everyone. I think that'd be really useful to have a look, for everyone to have a look. Yeah. Okay, I think we can get started. Any ideas? Okay. Yep. So we probably would know that the smallest value we can get is if A, B, and C are all equal just by the AMGM inequality. So what we want to do is like we want to prove this, right, with the AMGM. Any ideas? Okay, yep, I'm seeing some good ideas. Okay, yeah. So there are a lot of ways we can do it, but they'll probably all use the AMGM inequality. So how I'd probably use it is if we just look at the left-hand side, right? Like LHS will just stand for our left-hand side. And if this is our okay, let's do this a little bit. What would the arithmetic mean of these three numbers be? If we just think of them as a sequence of numbers and they're positive real numbers, we can kind of just get it by, as we did before, right? So n in this case would be equal to 3. And right, so this is our arithmetic mean, right? And what is our geometric mean? It would, because n is equal to 3, it'd be a cube root, right? And then what would want to do is just times everything together. Yep, and then we can simplify geometric mean like by quite a lot, right? Can we cancel out some things inside the cube root? Well, okay. Yep, we get something like this, right? BC times AC. But if we simplify that further, it's basically just this, right? And that is just the square root of 1, which we know is 1. And by our AM-GM inequality, we know that AM is greater or equal to GM, right? So that would mean AB plus BC. Like this part over 3 should be greater or equal to 1, right? And then we just times both sides by 3, and we get our equation. Right? And that's all. That's basically how we'd solve it. It could be really useful if you actually just considered, okay, what is the AM of these numbers that are involved? What is the GM of it? And then just compare both sides, right? And then a lot of the time that will just be enough to solve the problem. Any questions or anything? Okay. Then we can move on. So that's basically all we really need to know about the AMGM. And the AMGM is very easy to prove for n equals 2. So I will leave it as an exercise to the reader. If you want to like consider when n equals 2, how can you prove that the AM is always greater or equal to the GM? We have non-negative real numbers. It should be pretty easy and you can use the trivial inequality like we did before. Okay, now we'll move on to the Cauchy-Schwarz, and it's a bit of a mouthful, but basically it is also for non-negative real numbers, but in this case, we kind of have 2 sequences instead of just 1 sequence. And what it states is, as we see below, it means that we have a sequence of A1 to AN, and then another sequence of B1 to BN. And notice that these are sequences of the same length. What the inequality states is that the square of A1 plus the square of A2 all the way to this plus the square of AN times like the square of B1 all the way to the square of B2 is greater or equal to if you paired each one a number from the A sequence and B sequence together into pairs and then added those together and squared it. So that's basically what it means. Like, if I try to explain it in words, it's a lot more confusing. But if you just look at the algebraic expression, it should be a little bit clearer. And what I will point out is that equality can only hold if the ratio between A1 to B1, A2 to B2, all the way to AN to BN is the same. So their ratio, or we can consider it as like the fraction it forms, should be all the same. And yes, this looks very complicated, but it's actually very, very useful. Like, it's like one of my favorite inequalities. But yes, once you use it more times and trial a lot of questions with it, you get really familiar with it and you'll know how to use it a lot better. So yes. Okay. Does anyone have any questions towards like what the algebraic expression means, or can everyone like understand it? Even if you like don't know when you could ever use this kind of inequality, like does everyone understand of what it's saying? Okay, cool. And if we have time at the end, I can go back and talk about some stuff that from previous that people may have missed, but that's all right. We'll just move on for now. Okay, So I'm gonna assume that everyone at least like understands this algebraic expression. Okay, then we can try this problem. It's not very easy. It's like not easy at all. And especially if this is your first time using the inequality, it is gonna be like a bit hard, but we can go through it together. Again, I'll just give you guys like a minute to think about it. If you have any ideas, just type in the chat again. But yeah. Okay. Does anyone have any ideas? Yes. Okay. So I've seen some really good ideas. Okay. So basically we see that there are like 3 unknown variables, right? X, Y, Z. And what we can interpret these as is like one sequence. So this is a sequence of 3 numbers, right? But to use the Cauchy inequality, like you really need 2 sequences, but it hasn't exactly explicitly given us the second sequence, right? So what we can do in this instance is to construct another sequence. And you don't want to randomly construct it because it probably won't give you what you want since you want the maximum of this expression, right? But we can notice that the coefficient of x, y, z here is 1, 2, and 3, right? And we want to find the maximum. We want to find the maximum of this value, right? So do we want our expression x plus 2y plus 3z to be on the left-hand side of the Cauchy inequality or the right-hand side of the Cauchy inequality? Yeah, okay, so I'm seeing people say the right-hand side, and that's correct, because this is like the left-hand side is greater or equal to the right? So we want to make it, we want to construct our thing to make it that it's on the right-hand side. So let's say that like our sequence A1 is this. Yeah. Does anyone have any idea what B1, B2, or B3, like the corresponding, could be to help us solve this problem? Okay, yes. I'm saying like good ideas. It'd be quite smart to have it like this, right? Because that would make our right-hand side into A1. It'd just be x plus 2y plus 3z, right? And that's sort of exactly what we want. But of course, it's squared, right? And that doesn't matter too much because all we'd have to do is like square root at the end. Okay, so now we've got our two sequences. We can just put it into the Cauchy inequality and see what it gives us, right? So we just get x squared plus y squared. Okay, well, this is sort of what we want to prove, right? We want to prove this. Oh, actually, no, we already know it. Just let's say plug it into. Right, and it's really good because we've already been told that x squared plus y squared equals 1, right? Let's just change that out. So we get 1, then that's 4 plus 9, right? And then squared. And that gives us 14. Right? And then what do we want to do? We want to square root, right? We want to get rid of the power of 2, and then it gives us, right? And that gives us our minimum value, right? So, oh, sorry, my bad, maximum value. Yeah. Okay. Does this sort of make sense to everyone? Is there any steps that just don't make sense or anything? Also, do you remember you do have to square root? Because our right-hand side has a square in it, right? But it's asking us for it without the square, so we need a square root. But I think everyone gets like the gist of it, which is really good. You get a lot better when you use it a lot more, and it's really, really useful. Okay. I also will. When does equality occur? When can we actually achieve it to be square root 14? Okay. Well, it's basically when the ratio are all the same, right? And that's basically the yes. Okay. Yeah. So that would require x over 1 to be equal to y over 2 times z over 3. Yep. And then that would just give us what we need. And yeah, you can work out x, y, z, but okay, I think we can leave that. Anyways, okay. Now we'll move on to last inequality we have today. Unless there's any questions about the Cauchy inequality? Okay, I'm taking that as no. Okay, we can move on. So the rearrangement inequality. Okay, so it basically states that when you have, again, you really need two sequences of the same length, like we said before, and it's basically stating this algebraic expression below. So it's basically, you can think about it as pairing the big one from one sequence with the big one of another sequence, and pairing the small ones with the small ones is more efficient or more optimal than pairing like a big one with a small one and like, or pairing them randomly, right? And equality holds when A1 equals A2 equals AN and B1 equals B2 all the way until Bn. So, okay, this looks a lot more intimidating, especially the middle part, but we will go into this in more depth. Okay, so first let's cover what a permutation is. Right, so it says here that let something 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 be some permutation of sequence B. Does everyone have a good idea of what a permutation is? Okay, yeah. Okay, the pi part, it's really unnecessary. It's really just to rename it. Just think about it like a rename. I want to rename my variables, and it could be anything, but in this case, we really just chose pi. Okay, so it really doesn't have any direct meaning. Okay, yeah, so basically a permutation is just another, okay. Yeah, you can just think of it as a random naming of the sequence again, but it's the same numbers in it. We just want to reorder them. So a permutation is basically just a reordering, right? So in previously stated, we said B1 is greater or equal to B2, and it's greater or equal to Bn, right? So it's ordered from largest to smallest, right, with the number. But a permutation would just of sequence B would just be that we completely ignore this ordering. Like, we don't care about their size. We rename them and we reorder them. And that's basically what it means. We will be going over permutations, combinations, or the combinatoric stuff later in the course, but like for this question, the rearrangement inequality in particular just requires a little bit of understanding, and you can just understand it as like a random reordering. And it basically means that if A is still in order, we still keep the same order, so like 1 is the biggest and n is the smallest. And then we randomly pair it. Like, we randomly pair it with the numbers in B, then it's gonna lie somewhere in between pairing the biggest with the biggest and pairing the biggest with the smallest, right? This is like a little bit confusing, I can imagine, but just remember, like, big with big is gonna be better than like big with small. That's kind of the idea behind it, but we can think about it in a little bit more context. So let's say we have a pile of coins, right? It doesn't matter. Let's just say it's infinite piles of $1 and $2 coins. And the only rule we have is that we can take 10 coins from one pile and 20 coins from another. So what is the way that you can like maximize your earnings? Like, you want to make the most money. How can you do that? Like, just by intuition, you can share your ideas as to like how you want to grab the coins, right? Yep, so I'm seeing a lot of take 20 coins from the $2 pile and then take 10 coins from the $1 pile. And exactly, right? That's gonna maximize your number of, like, your amount of money, right? And that kind of works by intuition, but if you really wanted to explain why that is, you can explain it with the rearrangement inequality, because 20 is bigger than 10 and 2 is bigger than 1, right? So you want to pair the big with the big, so pair 20 with 2 and then just pair 10 with 1, and then that's going to give you the most money. Then what about like the least money? And you have to take the coins. So you have to take 20 coins from one pile, and you have to take 10 coins from another pile. Like, what would you do to make the least amount of money? Yeah, you do the opposite, right? So you'd take 20 coins, which is the bigger number out of 20 and 10 from the $1 pile, and then 10 from the $2 pile. And that's going to give you your minimum amount of money, right? Yeah. Okay, so that's basically the rearrangement inequality in some context. But let's look at it in an actual problem. So the problem below. So a cubed plus b cubed plus c cubed is greater or equal to a squared b plus b squared c plus c squared a. And I'll give you guys a little bit of time to try it. And a tip I'd give you guys is probably form two sequences, right? So it isn't explicitly telling us, oh, what our two sequences are, but you can sort of use like what you've been given to your advantage and like construct two sequences that are going to help you solve the problem, right? I'm seeing some really good ideas. Okay. If everyone's had a good look at it, then I'll just move on to it. First, we haven't been exactly told which one's bigger out of A, B, C, right? Like we don't know which one's exactly bigger, which one's smaller. Right? Okay, cool. Yeah. So in this case, what we can basically do is let's just log it. So what this stands for is like, okay, you don't have to use it, but it's really handy and it makes you look smart. It basically stands for without loss of generality. So because we noticed that these are of the same form, right? A, B, C are basically of the same form. And then over here, it's just a squared with another, like one variable. We can kind of just, without loss of generality, say like A greater or equal to B greater or equal to C, right? But we do have to have that equal to because there is a possibility that they're all equal or two of them are equal. So let's just say that without loss of generality, A greater or equal to B greater or equal to C. Then what could our two sequences be, right? So I think the more obvious one would just have like a sequence of ABC. And what could our other sequence be? Yep. Okay, our other sequence would be something like this, right? That'd be the most beneficial to us and make our lives a lot easier if we did this sequence, right? So now we have our two sequences. We kind of just want to, like I said before, pair the big with the big, right? So we know that this, right, it follows quite like trivially that A squared greater equal to B squared equal to C squared, right? Especially since our numbers A, B, C are non-negative real numbers. Yeah. Okay. And then by the rearrangement inequality, you would just pair the big with the big and would get something like this, right? We know that this is probably going to be our biggest combination. But what about the other side? Like, we can't exactly say it's the smallest combination because we're not pairing the smallest with the smallest, right? I mean, the biggest with the smallest, sorry. Yeah. Okay. So we're basically taking a random ordering of ABC, right? So our smallest would be pairing A with C squared plus, but we're not exactly doing that, right? That's not exactly our left-hand side. What we're doing is, let's say we kept ABC the same, right? We're randomly pairing them up. We're basically taking a permutation of our second sequence, A squared, B squared, C squared. So that would be like we just happen to choose c squared. But the rearrangement inequality should still be true, right? Even for a random permutation. Because we know that no matter what, this is still going to be bigger equal to, right? You can't really go bigger than that. So yeah. Any questions towards how we did it? What would we say, like, okay, let's add a little bit more to this question. What would we say that this is greater or equal to? What would come on the other side? If we want to find the smallest. Well, we could just pair the biggest with the smallest, right? And then that'd give us a with c squared. B with b squared and c with a squared, right? And then we'd get this. Yeah. Yeah. And then that's just, yes. Any questions about this question or this problem? Yes. So I'll say again, permutation is just some random reordering of our sequence, right? Because before we made this assumption that they're, okay, yes. So, and smallest is when you pair the biggest of one sequence with the smallest, and you just keep going in that kind of like, you'd pair, the smallest would just look like this, right? You basically take the smallest with the biggest and biggest with the smallest, and at the in between you go like, yes, you reorder it like that. But permutation, like I said, it's just a random reordering. Like it's basically when you kind of ignore that size thing we use in the rearrangement inequality, and we say like size, we don't care that much about it. We just randomly pair them together, and that's a random like permutation of it. Yeah. Okay. That's basically all. I think the most important part is probably knowing the biggest variation and the smallest variation. Like the middle part, it's very useful, but like it kind of comes as long as you know which one's the biggest, which one's the smallest. Like any other random permutation is going to be like, you know, the relative size, right? So that's all good. Okay. Okay, and I believe that is